All right, let's go ahead and take a look at our vectors here, the introduction to vectors worksheet. Vectors are really important in physics just because we can use them to represent all sorts of different things aside from direction. It could be that we're representing distance, could be that we're representing speed, any number of different things. So they're useful. So get to know them, get to love them, and the unit will go a lot easier. Not saying that you can't get through the unit without understanding what vectors are and how to use them, but it will make your life immensely easier if you do understand how to use them. All right, so let's go ahead and take a look at this. Only force that's acting on a projectile, it is gravity alone. Right. Once a projectile is left my hand, let's say we've got like a little dude throwing something off a cliff here or something. As soon as that projectile has left his hand and it continues on, the only thing that's acting on it is gravity. So that actually make more of a path like this because gravity would be pulling it down. Of course, there is air resistance and some other stuff, but we're not really concerned about that so much. We're just, for now, pretending like gravity is the only thing acting on it. 3 examples of projectiles. So you guys can notice that this is Miss Mardoyan's answer key, much prettier handwriting than mine and much more organized, so thank you to her for that. But 3 examples of projectiles, either I just plain old drop an object. I could throw that object up. Not like I ate too much throw up, but throw it up and gravity ends up pulling it down. At every single one of these locations, if I were to sort of mark out the path of this projectile at random locations, gravity would constantly be pulling it down here, down, 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 and down. So just keep that in mind. That's why it makes the arc pattern. And actually at the top of this arc is 0 meters per second, which is something that's kind of a hard thing to understand, which we'll talk about in future videos. All right, so let's go ahead and take a look at the last one here. We've got an angle that we could kick something at or throw something at, and that becomes a projectile once it's in the air. In this case, we'd actually have to break it down into a couple of components, and those are things that we'll talk about in the future as well. So just realize 3 different ways that we could do things, 3 different ways that we could have a projectile. I drop something, I throw it up and it comes back down, or I kick it at an angle, throw it at an angle, and it makes an arc. All right, once a projectile is in motion, it's inertia that keeps it in motion, its own inertia that it had to begin with, its mass in motion, right? Finding the term, we've talked about inertia a bunch, so see me if you need that one defined a little bit more. The main factor that influences a projectile is gravity, because that is the only force that's acting on it, aside from some more minor forces that we don't really get into, like air resistance, like I just said. Let's take a look at number 4. A vector is fully described by what 2 things? Magnitude, direction, right? Magnitude meaning maybe 50. And direction could mean, in this case, an angle. Right? Whatever this angle is, if this is coming off the ground, or my direction could be like we've been using in the past, negative or positive. Think of it as right or left, up, down, but just realize there's much more to it than just positive or negative like we've been doing in the past. And magnitude is just simply the number, so it could also be negative 50 or something like that for our number. Give 3 examples of a vector, so things like displacement, velocity, acceleration. If we want to go with non-motion related things, temperature would be considered a vector as well, because it can go up, it can also go down, it can go into the negative direction. Mass is not. Mass would be a non-example of a vector, because mass is either 0, meaning it's an object that doesn't exist, or it is a positive number. We can't have a negative mass. Number 6, vector diagram depicts a vector by use of an arrow in a specific direction. Again, the arrow should be something that is drawn approximately to scale. So if I were to represent a vector of 5 meters per second, it might look something like that. If I represent a vector of 10 meters per second, I draw it approximately twice as long as the other, and it visually helps me out a little bit. In most cases, it doesn't matter that we're drawn to scale unless we are actually trying to figure out a resultant by measuring, but it will help us out greatly if we do try to draw them to scale, just in terms of visualization. All right, next one. What's the net force? Sum of all forces acting on an object. We talked a ton about that. Another name for the result for a vector is resultant, right? Result is even in the word, so you can use that to help you out. 3 examples of vector addition. We've talked about these in class, but also realize that this is considered vector addition as well. and then I have to figure out what my hypotenuse is using a squared plus b squared equals c squared. Right. All right, we'll get into some more examples like that in a second. All right, so this this demonstration pretty much sucked, so don't worry about going to this site. If you did, you're welcome. Sorry I wasted your life, about 2 minutes of your life there, because it just didn't work out kind of how I had planned, how the other physics teachers had planned. On a computer, works pretty well. So if you're having a hard time with any of the concepts that we're going to discuss in a minute, you may want to go there. But on an iPad, just forget about it. All right, so answering the questions, the simulation here looks like we're walking for 20 steps to begin with in the north direction, so that's what's going on here. And then we're using the simulation to represent our path. Again, let's not really worry about the simulation, but then let's look at the next step. So next, we turn left, we walk 10 steps to the west, so that's where this 10 steps is coming from. We need to figure out what this resultant is, or the sum is, and that would be, again, one of those little a squared plus b squared equals c squared sort of problems. Doesn't matter which one is a, which one is b. Right? Just matters that neither one of these are c, because remember, c is reserved for the hypotenuse and the hypotenuse alone. So we know the answer already because it's in the answer key, but how we get there, let's go ahead and take a look at. So 10 squared is 100, 20 squared is 400, and then that is going to give me c squared. Oh, what is 100 plus 400? Very good, you're right, it is 500. I don't know why I said that. I've been watching too many kid shows with my kids. Not alone, of course. That'd be weird. So then let's go ahead and take a look at what the final answer is. We don't care that it's 500. That's c squared. We don't care about c squared. We care about c. So I take the square root of both sides, and we end up with 22.3 something something something, rounded off to 22.4, represents c. So represents our hypotenuse there. And of course, we could just reverse this and say c equals 22.4 if you prefer it written out a little bit more properly. There we go. All right, let's take a look at the next one. Does this property hold for vector addition? Yes. All right, 2 plus 3 versus 3 plus 2 is the same thing. If we were to do the same problem again, exactly like how Miss Mardonian has it down here, it would give us the same thing, right? Still have a squared, still have b squared, still finding c squared, just like we did above up here. Same work would hold true for down there. That looks like a mess. All right, let's move on. So we're going for a drive. Detour takes us out of the way. We end up driving all over the place. So let's see what's happening in this problem. All right, so to begin with, I go 10 meters north, and then so north for 10 miles, sorry. Thinking meters, we're normally in meters. Turn right and drive east for 5 miles. It doesn't even need to tell us that we turn right because east is in the rightward direction here on our page. At least we're assuming it is. North for another 3 miles. Then west for 10 miles. What's our resultant, right? How far from where you started did you end up? So from here to here, how far is that if we were to take a straight line path? So you can see the answer here. We're getting this answer from Pythagorean Theorem again. A squared plus b squared equals c squared. This right here is essentially our triangle. If you can kind of use your imagination, well, how do we get that? Well, rather than looking at it like this, why don't we just say, well, we go north for 10, north for 3, nothing in the south direction, so it looks like we're only going in the northward direction for 13 miles, so that's where we're getting this 13 from, because we're adding this 10 right here, this 3 right there, and getting that. Okay, and then if we think of things in the horizontal direction, think of our components in the horizontal direction, we're going 10 miles west, but 5 miles east. So of this 10 miles, we can almost think of it as 5 of those miles are consumed by the eastward direction, so we're left over with 5. And this is why if we draw things approximately to scale, it kind of helps me out a little bit, just visualize that. So then at this point, plug it in, a squared, b squared, we'll get c squared. So if we do the entire problem, b5 squared plus 13 squared equals c squared. This would be 25. This would be 169. That would still be c squared. 169 plus 25 is 194. And then we don't care about 194, we care about c. 194 is c squared. Take the square root of c squared, I get c. Take the square root of 194, because I did it to this side, I got to do it to the other. And I come out with 13.9 miles. And that's the answer that we come out with over here. Either way you do it, you get the same thing, but I would highly, highly, highly recommend that way of doing things. Like that way of doing things. It's kind of fun. All right, if we wanted to travel directly to our destination without following the streets, what angle would we take? There's actually a couple answers for this. You can see Miss Murdoin got 111 degrees, and I like the way she's thinking. She's thinking we're starting over here, and then we just walk off this way. I read it a different way. I read it as, well, what if we're down here, and we're walking up this way? That would be a different way of doing things then at that point. So, because we've got a couple of different sides here, and we're looking for an angle, we're basically looking for this angle up here, I can do some SOHCAHTOA. So hopefully you remember that. SO stands for sine of theta equals my opposite over my hypotenuse. CA stands for cosine of theta equals my adjacent over my hypotenuse. And then TOA represents tangent of theta is my opposite over adjacent. A bunch of you guys in class did a fantastic job with remembering all this from geometry. Super impressed. That's really good stuff. So we're gonna take a look at how we find this now, right? Because that's theta. That's the unknown angle. Well, there's a couple ways I can do this. There's 3 ways I can do this. I can use sine, I can use cosine, or I can use tangent because I have all my sides. The most logical one to use is tangent, though. The reason that is because I'm given my opposite and I'm given my adjacent. I had to solve for this hypotenuse from the previous answer, right, from part A. The problem is I rounded here, so I'm going to be a little bit off if I do use this. The other problem is, even if I didn't have to round, we've got to worry about if I was wrong, if this answer was wrong to begin with, then that automatically makes, even if I do my work perfectly down here, it automatically makes this next answer wrong. So could we use sine or cosine? Absolutely. It's not as logical as using tangent, though, because with tangent, again, we already know these sides. Because we know those sides are true, then we want to use it for that reason. So let's go ahead and take a look at that. Let's figure out what our angle is. Tangent of theta equals opposite over adjacent, right? Kind of like what I wrote out before. So I don't know theta. That's what I'm trying to figure out. So I have tangent of theta, and theta is just another variable, equals my opposite, which is 5, over my adjacent. At this point, I may not really know where to go next, but I can do 5 divided by 13 at least. Is 0.3846. I'd recommend going to a bunch of decimal places. 4 decimal places is probably pretty good. Just go ahead and round off at the very end after we've finished the entire problem. So I am left with tangent of theta equals this 0.3846. And now at this point, I can actually get tangent, theta by itself by doing the opposite of tangent to both sides. If I want to get rid of tangent, I do the opposite. Just like if I want to get rid of multiplication, I divide. If I want to get rid of addition, I subtract. All right, so I do the opposite of tangent. Well, what's the opposite of tangent? Actually, you have this key on your calculator. It's tangent to the negative first. If I do it to one side, I got to do it to the other. Okay, so at this point, tangent, the inverse tangent cancels with tangent, so I'm left with just theta. And then tangent, or inverse tangent, sorry, of 0.3846 is 21.4. Well, wait a second. I got 21.4, Miss Mardoin got 111. How does that make any sense? Remember, I'm assuming that I'm walking this direction. So instead of going up, I would just say, well, my angle is here. Miss Mardoin, on the other hand, assumed that she was going this way, so she did get 21.4, but then she added on another 90 degrees here, and that's how she got 111 or 111.4. She rounded it off. So just realize, because this problem wasn't very specific, we might get a couple of different answers, just sort of how we're viewing the problem. Okay? I'm going to skip these next couple of pages because it doesn't have any of the work shown. In the answer key, you have it exactly like this. All right, I'm doing the videos directly off the answer keys. So I'm going to go down to pages 5 and 6, which are a repeat of those two pages that we just skipped, except now they have the work shown. So what I would recommend doing is doing the worksheet and looking at your answers. If you get it wrong, do it again. If you still get it wrong, then realize, oh, maybe I'll come down here and actually check out the work, or hopefully listen to this video, or even better yet, come into seminar so we can talk about it one-on-one or after school. All right, so I want to figure out the scenarios below. Right, I'm drawing my vector, connecting it tip to tail. So tip to tail just means literally the tip of the vector to the tail of the next. So no matter what sort of things going on, what sort of scenarios going on, I'm always connecting it tip to the tail of the next, over and over and over again. Doesn't matter how many vectors I have. Okay, so I'm walking 5 meters east. That's what's going on here. 5 meters to the eastward direction. I turn and I walk 20 meters west. And then I turn and walk 10 meters east. So like Miss Mardoin has, she's got everything drawn to scale. Right? So it looks like I'm trying to figure out how much space is right here. If I draw it to scale, it's kind of nice because then it gives me a nice visual. Is this perfectly to scale? No, but it's good enough where we can get a nice visual from it. So if I'm going 10 meters in the eastward direction and 5 meters in the eastward direction, that means I'm going a total of 15 meters east. And I'm going 20 meters west. So it's like, well, which one's the winner? Well, west. How much is it the winner by? 5 meters. Or you can look at the work that Miss Mardoin has up there. All right, next one. If I run 50 meters due south, so I'm going down, turn, and I go 30 meters due north. So remember, due north and due south and due east, due west, it just means towards the. So due you could replace with towards the whatever direction. Okay? So then we turn and run another 10 meters due south. So 50 south, 10 south, it gives me a total of 60 meters to the south, but then we've got to take away the 30 meters that's going to the north, so we're left over with 30 meters to the south. Again, because it doesn't matter how I add these up, right? Because 50 minus 30 plus 10 is the same thing as 50 plus 10 minus 30. It's commutative property of addition. All right, so number 3, skip 40 meters due east and 30 meters due north. So 40 meters to the east, 30 meters to the north. What do I have to do here? So like it shows, we've got to do some Pythagorean Theorem. I don't know my hypotenuse, so that's my c squared, and it's coming from right over there. Doesn't matter if this if A is 30 or if B is 30. It's just if whatever one of them is, the other one has to be the opposite of that. So one of them has to be 30 squared. Our other term has to be 40 squared. Right, 900 plus 1600 gives you c squared. 900 plus 1600 is 2500. 2500 is c squared, though, not c, so we got to take the square root of both sides. And we're left with square root of 2500 is 50. Great problem to do, completely mental math, or maybe not necessarily mental math, but scratch work without a calculator. Remember, SAT's coming up. I remind you guys a bunch. You're probably sick of me saying it, but practice that mental math. I want you guys to be able to do really well for your own sake. All right, so this next one says we're cartwheeling 20 meters due west, 40 meters due south. Oh, it's another a squared plus b squared equals c squared problem, just like before. If you need more of an explanation, we can go over it. Okay, so this next part is a little bit more of a challenge because it brings together a whole lot of things from the rest of this worksheet so far. I hate calling it a worksheet because it's more than that. And this whole concept that we've been dealing with so far. All right, so let's take a look at what's happening here. So to begin with, I roll 30 meters due east. Right? So 30 meters due east would put me something like that. Go a little bit smaller here. So 30 meters due east, 10 meters due north. So notice I'm trying to keep these approximately to scale. You know, this should be about triple what I just drew over here. Again, not a huge deal if it's not, but it does really help us visualize it, so it's best if we can do that. Now I'm going 40 meters due west, so 40 meters due west would put me right over there. 20 meters due south, so 20 meters due south right there. And then another 10 meters due south. Just realizing in the original answer key we accidentally made a mistake and left this other 10 off. Then we're going 15 meters due west, so out that way. And then another 5 meters due north, so up there. And see, this is 10, this is 5, but I didn't draw it perfectly to scale, so that's okay. All right, so if you can kind of use your imagination, I'm trying to figure out how far that is. All right, well, it's kind of hard to visualize, but we can think of it as a triangle, right? And that's basically a hypotenuse, or we can think of it as a triangle this way, and then that's still my hypotenuse in the middle there. That's kind of hard. For some of us, you may be perfectly fine with that and be able to figure out what this side is and this side is, and then we could figure out what our hypotenuse is based on Pythagorean Theorem. But to me, that looks a little bit overly confusing. So why don't we try to go ahead and simplify that down? All right, so to begin with, actually, let's not even worry about to begin with. Let's just look at all my horizontal directions and see which way I'm going overall and by how much. So to begin with, I've got this 40 up here. So 40 in the westward direction. We could just say in the left direction. It doesn't really matter at this point. Then I've got 30 in the opposite direction. So that means 40 is the winner by 10. Right? It's going, so far I'm going that way by 10. All right, then I deal with this other 15 down here. Now if I've got 40 going this direction, 30 going this direction, and then I'm dealing with another 15 going the other direction. We can take all this and do some vector addition with it, right? So 40 plus 15, I'm adding those up because I'm going in the same direction. Gives me a total of 55, right? 55 that way. Well, I've also got this 30 that's going back the opposite direction. So 30 going back this way. So that means I got to get rid of 30 of that 55. So I'm left with 25. So in my horizontal direction, I've got a total of 25 meters, well, which direction did I have more of? Looks like to this leftward direction or to the westward direction. Okay, well, that's not my answer yet, right? I've still got to deal with the other side of things here. Let's go ahead and get rid of that. Other side of things here being my vertical directions. Okay. So, vertically, I'm going 5 meters up. Oops, still on the big pen there. Going 5 meters up. 5 meters up. There we go. 10 meters up. So that's a total of 15. And then in the downwards direction, right, I'm here and here, that's where I'm getting these numbers from. In the downwards direction, I'm going 20 down, 10 down, so that's a total of 30 down. Oh, 30 down, 15 up. Down's the winner by 15, so to speak. So now that's what I can deal with. A little bit easier than looking at all this stuff over here. It's much simpler if we just say, you know what, let's forget about all that and go with what's there. All right, we've simplified it down quite a bit. Now that's not my final answer, because my final answer is asking me what is the overall distance that I traveled. At this point it becomes an a squared plus b squared equals c squared kind of problem. Right, so 15 squared plus 25 squared equals c squared. 15 squared is 225 plus 25 squared is 625. Oops. And that equals my c squared. The next part is a little bit more challenging to do in your head. Not that you can't. My mind shot from the day though, so I'm going to go ahead and plug it into a calculator here. And I get 850. That is embarrassing. I should have been able to do that late in the day or not. C squared. So that's where my 850 is coming from. And then let's go ahead and take the square root of both those sides. And I find that the square root is 29.15. So C equals 29.15. And of course I could then take this answer, plug it back into Pythagorean Theorem. Have my a squared, my b squared. We already know what that is. It's 850. I should be able to square this to plug it back into C, and I should get somewhere around the lines of 850 equals 850 if I plug it back into my formula to go ahead and give it a proper check. Alrighty. Alright, so we are just about there. I won't go over the last page entirely because all the work's there. Most of the problems are identical to some of the other ones that we've dealt with in the above problems. Alright, so this one's a lot different though from what we've seen in the past. So this one I want to go through entirely together here. We did it in class. You may need to see it a couple more times, or if you were absent, give it another shot. So, sorry, if you were there and need to give it another shot, go ahead. If you were absent, watch it the first time around. Alright, so it says Roy punts a football with a velocity of 40 meters per second at an angle of 50 degrees north of east. Okay, weird, but let's take a look at what that means in a second. What are the x and y velocity components of his punt? And we're given a hint here. We hopefully don't need the hint, but it is nice to have. We know that we're dealing with something with an angle, and we're dealing with some sides, so we know that it's going to have to be a SOHCAHTOA type thing or some sort of trig that we're dealing with. Okay, so let's go ahead and take a look at what's happening here. All right, so it says we punt a football with 40 meters per second with enough force to cause it to go at 40 meters per second, an angle of 50 degrees north of east. Well, east is this direction. North of east would be somewhere over here, above east, north of east. And it's 50 degrees north of east. So this angle right here would be 50 degrees. So that is my theta, right? Theta is 50 degrees. Okay, so let's go ahead and take a look at excuse me, what we need to do here. So I already know that I kick it with enough force to cause it to eventually get up to 40 meters per second. It's in the air, and the reason that it's in the air is because it has some lift to it, and it's moving in this direction as well. So really we have to break this down into components, because this number, this 40 meters per second, comes from the fact that I have some velocity in the x direction and I have some velocity in the y direction. This is essentially my resultant. So I know my resultant to begin with. Now I'm trying to figure out the reverse. I'm trying to figure out what my components are. Okay, so there's a few ways that we could do this. I'll show you the one that's similar to what's in the answer key, so we just kind of follow along with that. But to begin with, I've got to figure out, well, what is either my opposite or my adjacent. So you can kind of pick either sine or cosine, because we don't have our opposite, we don't have our adjacent, so we can't do tangent. Because I have my hypotenuse, I can use either sine or cosine. So we've got sine of theta equals our opposite over our hypotenuse. In this case, I have what my theta is, sine of 50. This is nice. We don't have to deal with any sort of weird inverse sine stuff or inverse trig stuff, which kind of gets to be confusing sometimes. Our opposite we don't know. Opposite being across from the angle, and our hypotenuse is 40. So if we do sine of 50, whatever the answer is there, and then multiply it by 40, I'm going to end up with my opposite equals 30.64 meters per second. So what that means is, of this 40 meters per second, the reason I'm getting that is because partly I'm going in the y direction. I'm going in the y direction with 30.64 meters per second worth of speed. But I'm also traveling in the x direction, and that's what we're going to take a look at now. What's my x direction here? All right. So I can do that a couple of different ways. Deal with cosine, or deal with trigonometry at this point. I could say a squared plus b squared equals c squared. I know c, right? 40 squared. And I know either a or b, right? Doesn't matter which one that is. And now I'm just solving for b squared, right? So we end up doing, whatever 30.64 squared is, subtract that from 40 squared, which is 1600, take the square root of that, and I have b. Or the other way, and this is the way that's actually in the answer key, if you go to take a look at that, use my trig. Cosine of theta equals adjacent. Adjacent just next to. Realize this is also next to, the hypotenuse is also next to, but the hypotenuse is different. When we're talking about adjacent, we're talking about adjacent sides, not hypotenuse. Equals my adjacent over my hypotenuse. Cosine of 50. Again, we know the angle. We're using the same angle that we did before. My adjacent, I don't know, but I do know my hypotenuse. Same hypotenuse as we used before, and identical in terms of how to solve it from here. Do cosine of 50, come out with your answer, multiply both sides by 40 to get x by itself, and I would come out with x is equal to 25.71 meters per second. So, 25.71 meters per second. So at this point, I would say you're not done. I mean, we kind of are, but I would say your last thing that you want to do is now take these numbers, plug them into Pythagorean Theorem. A squared plus b squared equals c squared. We'll do our little check step here. So it'd be 25.71 squared plus 30.64 squared equals 40 squared. And then whatever this is plus whatever this is should equal somewhere around 1600. If it doesn't, then we know we've got to go back and give it another look. All right, so last few. These ones I won't go over in depth because it's pretty much identical to what we've done in the past, just more practice. Get down to this one, realize it's telling us that we've got to deal with our velocity, magnitude, and direction. The weird thing about this one though is it says Huck Finn walks at a speed of 1 meters per second across his raft, perpendicular to the raft's motion. So if this is my river, sort of here, this is almost like a top-down view. The raft's coming this way, raft's coming this way at 2.5 meters per second. Huck Finn is walking this way across his raft, so he's going to end up looking like from above that he's making that resultant. All right, rest of them, give it a look on the answer key. You should be pretty good. If you need to, come on for extra help.